research, teaching, outreach. How do you combine them all and impact hundreds of students? Basically, we're trying to ask students, how can they help find aliens? So let me tell you about some projects I've done. The first one was in the UK. Clara Sousa Silva really initiated this project, had the brainchild, thank you. I served as a mentor for a research project and then took over as coordinator. So here we actually worked with high school students where our goal was to work towards publishable research. The second project was in SciEx at UNSW, and here it's much more involved with individual students actually had a research project that they did for high school. And our goal was to support them in that research project. And I co-developed the program and it started in 2020. So I'm going to use these two as an example of what I'm going to talk about. So the first question and the evidence that this is an effective thing to do is I want to ask you, how much do you feel like a scientist? And consider what the students said. And in 1 week online, deep engagement, we managed to, on average, increase the sense with which our students felt like scientists from 3.8 to 4.7. So that big impact on students' confidence, on students' sense of skills, sense of identity was achieved so quickly. And it's really an achievement that they feel. So it's the challenge that is a source of pride and can often impact where they're going to go in the future, hopefully. So the benefits for the student is really the engagement, the deep engagement with research. So they actually get to see lots of different branches of science and the ability to ask lots of questions. So this is the Australian of the Year, and they got to interact with it, which was awesome. Computers, we know, are very, very important for modern research. And I have to say, one of the most important skills I think I teach them is how to use Excel. And it's really, this is part of changing their perceptions of research and getting a more authentic idea of what does it mean to be a scientist in practice, and really dispelling those myths of, old scary white men in lab coats. One of the students said, oh, they're just nice, normal people that happen to know a lot about one particular topic. And I thought that was cool. The benefits for mentors, I think that's really important, that the mentors gain supervision skills, management skills, communication, teaching, all sorts of transferable skills that really expand their CV and empower them to go into academia or go into industry, wherever they want to go. And I can talk from personal experience here. When I was a mentor, I learned how to teach, I learned how to supervise, and that put me in such great stead. For example, this photo at the bottom with my hand on the mouse, never do that. And I learned that in this sort of process. Now, the problems, obviously money, how do you make it work? And how do you find the time? Academics and really everyone at university has 10 million things to do and 10 million not enough time in the world. So what are you going to do? How do you make it work sustainably? I don't have all the answers, but I've learned heaps about how to make it work, and I want to share that with you today. So there's 4 areas. I'm going to focus on really how you choose your project, and specifically in the context of this conference, so spectroscopy, and how do you promote that to students? And just say a few notes about the other things because I think they're really important structurally. Feel free to email me to ask for some more details if you're thinking about setting up a program like this, or if you have any questions. So, team structure. The way I think it works best is you have a coordinator who really organizes everything. It's a lot of work. And then you have an executive team who's there to bounce ideas off, help out with things, make decisions, get funding, that sort of stuff. You've got academic leads who have the research project and have the risk safety authority over the PhD students. So ultimately the PhD students are really the ones that engage with the high school students most. They're the ones whose time is most significantly impacted. Hopefully the academic leads help for 1 year and then it moves on. And sort of an hour a year, which is acceptable. And then the high school students we found the ratio that works pretty well is about 6 students per 1 mentor. You can have 1 to 3 mentors, so bigger groups. It actually works really well. The economies of scale work in our experience. So the project selection. I've come up with a fancy acronym because I've been around too many astronomers. Publishable, and it doesn't need to be publishable, but is it novel? Is it useful for your research, telling you what directions to pursue and what directions are just don't go there? The resources available. So can you just use a web browser? Do they need to load a terminal? Do you need a fancy lab with really expensive equipment? To what degree does each individual student have ownership of the project? And that really directly competes against publishability. If the individual student has ownership, you probably can't make it publishable particularly easily. The background required, how much do they need to know to start your project? And also consider how much of that is just generically useful information that they'd learn in a science degree that you're pre-teaching. There's stuff that we love it, but honestly, it's a bit specialized and not really going to be useful for them in the future. And finally, and I'd say most importantly, what's the excitement factor? Why do students want to pick your project? How excited, how interested are they? How much can they tell their grandmother, oh, I'm doing a project on blah-de-da-de-da. And that's where Finding Aliens come in, because that one's got the excitement factor. Okay, so I want to start with a project that many of you might be familiar with. This is a Marvel project, and yes, academics do this a lot of the time. You may have seen many talks on that at this conference, but we've actually worked with high school students to help out with some of the aspects of this project. So a lot of it is actually searching the literature, digitizing the literature, especially the old papers. Experimentalists in modern papers, please put your supporting information in. It helps out a lot to make your research relevant and used more broadly. Thank you. And then you take all the assigned transitions, you use a program called Marvel, and it extracts out the energy levels. They're used to figure out line lists, potential energy curves, all the sort of properties you want. And I've actually worked with high school students to publish 2 papers. So I did it for 2 years, 2 papers, good success rate, obviously. I will say that I'm first author here for a reason. There are quite a few student authors and they were very useful, but you needed someone to put in serious amounts of time to make it publishable, to bring all those little bits and pieces together and turn it into a paper. Be aware. This is just a nice graphic to illustrate the connectivity between all the different vibronic states rather. But if we consider our probe, the publishability is very high, obviously. The resources are easy because there's a browser implementation. If you can make it on a browser or you can make it a GUI, very easy. The ownership is low. Each group of students does 1 molecule, and if you ask them each to write a report, it would be hard. The background, astro is cool. I think that's fun. Spectroscopy is necessary for future careers, so I feel fine teaching them that. And as much as I love quantum numbers, it's not really that important for them. So that's sort of an auxiliary thing you have to teach them to be useful, but not that important. And I would say the excitement factor is high. You've got to find the right molecules. I would say moderate to high, depending on things. And then I want to talk to you about a project that didn't work as well. So this is the diatomic constants project. And if anyone's read Huber-Herzberg or the NIST Chem Webbook, you've got the constants of, I think it's about 1,000 molecules. And I said, well, we've got lots of students. Give each student a molecule, put some lectures together, get some collaborative, Google Sheets, put an online database that they can enter. It'll work. Lovely. No. And the reason I think it didn't work is, one, the structural elements weren't in place. The students coming in, I actually did a summer school in the UK. The students coming in didn't know that this was what they were doing, despite I did tell them, but they didn't listen. You need to make sure your students are engaged with what you're doing and motivated, or it's just going to fail. But more broadly, I don't think this project idea is as compelling as some of the other ones I've done, because it's a collation, so it's okay, publishable. There's a website, so that's okay. It's reasonable. Finding papers, if you're not on camp, just be on campus. The ownership, I hoped that it could be high, but I think I overestimated this. Students didn't get excited about individual molecules that they could call their own. The spectroscopy was useful, but the quantum number details, there's actually a lot to it that's not really relevant for many students. And really the killer, I think, is the excitement. Trying to convince students that this is important is hard. But on a more positive note, I actually want to tell you about a project that I did in Australia, the approximate spectroscopy of biosignatures. So we've got AT over here, obviously. And this is all based around this program called IQMol, where you do computational chemistry. You put in a molecule, this is glycine. You say, run a geometry optimization of vibrational frequency calculation, and then you can get some animated vibrational frequencies. Students can actually see it, and then they can produce a spectra. And the knowledge required to do this, the astronomy is fascinating to them. They love learning about biosignatures. The comp chem, you keep it simple. Just tell them what to use. And then the spectroscopy is useful for them. And actually in Australia is part of their HSC, their year 12 syllabus. So it's useful. So each student actually designs their own set of molecules, chooses them, and determines their research questions. So we've had some students going, how could you detect technosignatures? How could you find amino acids in an atmosphere? And there's a million one problems you can solve, and each student can really get ownership. So if we look at Pro, the publishability, I think, of the original ones is quite low, but I do say it's been very useful to test ideas and prepare for a PhD project, because I got all my, that didn't work out of the way beforehand. And it doesn't matter for the high school students. They'll have a project, even if it's not publishable. The resources are easy because of IQMol, just increases accessibility so much. The ownership is very high because they determine their own question. And the background, I think, is fine. The background's interesting, it's relevant, and the excitement level is really high. So this is the project I'm doing at the moment. I really love it. I think it's very effective, and maybe it works for, or can be adapted for your sort of environment. Love to chat to you about it. So I did want to go back just briefly and touch on the program structure. Consider, do you want a 1 week summer school versus regularly throughout the school year? 1 week summer school is so much easier on your life, I would say. You want to consider, are research projects an elective, so part of the curriculum, or are they extracurricular? That just affects the motivation of your students. Do the students need individual projects? So SciEx was really designed because each student needed a project they could write a report on. And is group work okay? Then maybe you aim more towards a publishable result. Funding, consider your expenses, and really there's startup costs when you're developing the project resources, when you're developing the program, versus your ongoing costs that year on year on year on year you have to spend. Look, from my point of view, the main cost is paying your PhD students. I don't want to get into a rant, but pay them as you would pay them if they were teaching, because otherwise we'll promote inequity. Your income, student fees can actually be a really important part of the process, because otherwise it doesn't go round and doesn't keep rolling. But you need to include, I do 25% fee waive places for the students that can't afford to pay. Think about whether universities, governments, schools, research groups, etc. can pay. I have to say, I think Australia is it's really difficult here, because there's not that culture of outreach. There's not that culture where governments and schools are forced to give back money to the community for equity, diversity and inclusion, and that makes it hard. So in the UK, in comparison, there was actually that mechanism. Universities had money to spend on these sort of things, and it really helped. So I'm trying to talk to government and get them to fund outreach. No idea how successful they'll be, but something that you need to consider. And so I've shared with you here what I've done, what I've worked, what didn't work so well, hopefully giving you some ideas. But I want to know, what did you do? Let me know. Thank you.